Okay, welcome back. This is the second video, and in this video what we're going to do is talk about the rotational inertia of simple shapes and the parallel axis theorem. Okay, so let's start off by just remembering that the last time we talked about rotational inertia, we were talking about a point mass that was rotating around an axis at a certain distance r, and we determined a formula for the inertia. The formula was simple. It said that the inertia is equal to mass times r squared. And this was a pretty simple situation because it was a point mass. So you can actually generalize rotational inertia, and you can calculate it for shapes that are, for any shape really, but for simple geometric shapes, you can pretty easily come up with formulas for rotational inertia. Now the table that's shown here is table 9.2 in your textbooks. And this table lists a variety of simple shapes, and it also gives a formula for the rotational inertia of each shape. So for us right now, it doesn't matter where the formulas came from. What's important is that each one can be applied to any particular shape if you are rotating it around a certain axis. So for example, the very first example, a slender rod in case A, would be like a pencil. It's something that you're assuming is uniformly constructed. It has a constant density. And if you place the axis of rotation so that it's perpendicular to the length of that rod, and it passes through the rod's center of mass, then the inertia of the rod is going to be given by the formula 1/12 times ml squared. Okay, so m would be the total mass of that rod, and L is the total length. So the dimensions of the inertia are still going to be mass times length squared. And the formula really only applies to the case where you place the axis where it's shown. So what would happen if you were to move the axis of rotation to the end of that rod? Well, the first thing you would expect would be that the rotational inertia would increase because effectively you're moving more of the mass away from the center of rotation. And if you look at the formula in part B, you can see that the rotational inertia is larger. You went from 1/12 to 1/3. And so that should make some sense. So you can apply similar types of arguments to the rectangular plate. Obviously, you can place the axis of rotation anywhere you'd want, but usually in a table like this, they will place the axis of rotation in a fairly simple place, like through an edge or through the center of mass. As you see in some of these pictures. Down underneath you see some more examples. Cylindrical symmetry is going to be very important for us. You've got 3 different cases there. Notice that when you go from the solid cylinder to the thin-walled cylinder, in other words when you go from case F to case G, you can see that the rotational inertia doubles. You go from 1/2 mr squared to mr squared. And that should make sense because the mass is being moved further away from the axis. The same thing can be applied to the sphere. For a solid sphere of mass m, the inertia is 2/5 mr squared. If you were to take all of that mass and distribute it along the edge or the outside, then the rotational inertia increases to 2/3 mr squared. So for some problem solving, a lot of times you can use a simple geometric shape as an approximation to something that's more realistic, and we'll be doing that. Now let's follow up with something called the parallel axis theorem. The parallel axis theorem is going to be useful in a case where you would like to move the axis of rotation and make it any place. In other words, what if you want to have an object rotate around an axis, but it's not one of the axes that was shown in the table? There's a very simple way that you can do that, and the simple approach is that you basically take the rotational inertia around the center of mass and you add to it a second term, which is the object's mass times the distance the object has been moved. So here's an example. Let's say that you have a solid cylinder. The rotational inertia of a solid cylinder rotating around the axis through its center is given by the formula 1/2 mr squared. You can look that up in the table. Now, what if you were to take that solid cylinder and move it a distance d away from a new axis, a parallel axis? what would happen to the rotational inertia? Well, I hope that you can appreciate the fact that the rotational inertia will definitely increase because you're moving mass further away. Now, the way that you would calculate this would be to use the parallel axis theorem. Since the new parallel axis is parallel to the original axis that we talked about, the axis of symmetry, you can calculate the new rotational inertia simply by adding 1/2 mr squared plus md squared, where m is the mass of the cylinder and d is the distance of the cylinder's center of mass to the parallel axis, and that's shown in the picture. And that's really all that you have to do if you're calculating rotational inertia for a simple shape and you want to move that shape away from the axis. Now, I'd like to finish with just one example here that's kind of neat. This is an application of the parallel axis theorem. If you go back to the uniform rod, a length L, mass m, we can look up and we can find out that the inertia is equal to 1/12 ml squared for this particular case. Now, that's the case when the axis is perpendicular to the rod and it passes through the center of mass of the rod. So, a question might be, what is the inertia of this rod if it's rotated around an axis parallel to the one that's shown, but passes through one end? Okay, so if you move that axis further down. So we can apply the parallel axis theorem, and we can calculate it. It's going to be equal to the rotational inertia around the center of mass axis that we see up above. And then we're also going to have to add the md squared term. So we're going to be adding 1/12 ml squared plus m times L over 2 squared, because we're effectively moving the rod by a distance of L over 2. Okay, so the rod's center of mass will be a distance of L over 2 from the new axis of rotation. So when you evaluate this, you find that the new rotational inertia around this parallel axis is equal to 1/3 ml squared. And so there's a picture here that also shows what we've just done. There's the axis at the end of the rod, and we've just figured out the new rotational inertia around that axis. 1/3 ml squared is bigger than 1/12 ml squared, so that should make sense. And the other nice thing is that our expression agrees with the expression in the table. If you recall, in table 9.2, the second figure actually showed us this particular situation. So we've just kind of verified one of the formulas in the table. And this is a nice example of how you can apply the parallel axis theorem. Okay, so I hope you enjoyed that, and hopefully we've just shown how you can use rotational inertia for simple geometric shapes, and how you can apply the parallel axis theorem to moving the axis of rotation. Okay, see you later.